Okay, one more property that I'd like to spend a little bit of time talking about is called viscosity. And that's because it's going to be an important, the property itself is important, but also its implications in how we analyze fluid flow are very important, and we're going to see those throughout the course. So it's worthwhile to spend a little bit of time on it. And I think we all have kind of a basic idea of what viscosity is in terms of this idea of resistance to flow. So for example, honey we'd say has a high viscosity because it flows very slowly when we try to pour it out of a container, whereas water pours very quickly, so we could say that has a lower viscosity. But we can maybe think about that a little more precisely for the purposes of this course. So I'm going to draw here simple geometry. So these are two plates, two flat plates that are separated by some distance h. The bottom plate is stationary, and the top plate is free to move. And in between these plates is some fluid. You can imagine whatever you want. Maybe water is a good picture to have in your mind. And so the top plate is free to move, and it's moving at some velocity capital V. And I've drawn a coordinate system such that the forward direction is x and y is positive from the bottom plate upward. So the x component of velocity v sub x is capital V. And so the question is what is happening to the fluid in between these plates. I've kind of drawn some idea of what might be happening, but we can think about that and see if that makes sense. So the first step is to make some observations. So the first observation is that the fluid at the boundaries, the two boundaries, at the upper and lower plates, moves at the same velocity of the boundaries. So for example, at the lower plate, which is stationary, the velocity of that plate is 0. So it makes sense that the velocity of the fluid immediately adjacent to that plate would also be 0. Similarly, at the top, this plate is being pulled so that it's moving in the x direction at a velocity v. So the fluid that's immediately in contact with that plate is probably also moving with that same velocity. And so this is kind of intuitive, but this is what we call the no-slip condition. And actually it seems intuitive, but there's details about special kinds of fluids or special kinds of flows where this boundary condition may not be 100% valid. I think there's even some controversy about that, even today. But for the purposes of this course, we can assume the no-slip boundary condition is valid. So at these two boundaries, the fluid is moving at the same velocity as the boundary. So the atoms or molecules that are right adjacent to the boundary are going to be moving at the same velocity of the boundary. Okay, so then the next observation we can make is that because we have these two boundary conditions, 0 and v, then the fluid velocity inside this gap has to change from 0 at the bottom to v at the top. So there has to be some change in velocity to go between these two boundary conditions. I haven't said what the characteristic of that change is, but it has to change from 0 to v. Another observation we can make is that for many fluids, if this gap h is small, then this variation in velocity can be approximated as a linear variation. So in other words, the velocity increases linearly as we go up in y from the bottom to the top plate. And we can write this, we can write an equation for this, right? If the velocity at the top plate is v at y equals h, and the velocity is 0 at y equals 0, then the equation for this velocity profile, vx of y, is y v over h. And you can see this satisfies the boundary conditions. At y equals 0, the velocity is 0, and at y equals h, these h's cancel, so the velocity is v. So this equation expresses a linear variation in velocity, a linear increase as we go from the bottom plate to the top plate. So this is an example of what we call laminar flow. So in this kind of flow, these fluid paths are straight lines. There's no mixing or there's no tangential component to the motion. And so one way to think about it is like a deck of cards. If you slide a deck of cards, each card moves forward at a velocity that kind of maybe looks like this, right? The top card will move with the velocity of your hand, and the bottom card will be stable. So this is what we call laminar flow. The opposite case is what we call turbulent flow, where there's less order or more disorder to the motion. You have not only motion in the forward direction, but you have motion in the tangential direction, a lateral to the flow. And this motion has a complex characteristic that's hard to describe. So this is an example of laminar flow, what we've shown here. Okay, so given this simple description of this flow field that we've shown here, how exactly does one layer that's moving in this laminar flow, how does it pull the others with it? What's the relationship between the motion of one layer of fluid and the motion of the other layers of fluid? Okay, so I'll go to the next slide here and kind of redraw the picture that I had on the previous slide so we can refer to it. Again, we've got two plates separated by a distance h, and we said if h is small, then we can approximate this velocity profile as a linear one going from 0 at the stationary bottom plate to capital V at the top plate that's free to move. And we want to know, or try to figure out how these different layers can interact in a way that allows, you know, one layer to pull another layer with it. Okay, so let's make another observation here. And so this observation is an important one. And so this observation states that the shear stress in the fluid is linearly related to velocity gradients. And a velocity gradient, remember what a gradient is, it's a slope. So the velocity gradient is the slope of this velocity profile. We can write that mathematically in the form of an equation, and I'll do that up here, and then I'll talk about it. So this equation is a shear stress, and I've written it as tau yx, and I'll explain that in a minute. The shear stress is equal to the velocity gradient, dvx dy, so that's the slope of this line, basically, if this is a linear function, but if it's not linear, it's the local slope of this velocity profile, times some constant, eta. This is the Greek letter eta. And this constant is called the viscosity coefficient. And this equation is called Newton's law of viscosity. So it's one of those relationships, kind of like Hooke's law, you know, for a spring, F equals kx. The force is related to the deformation. Here, for a fluid, we're saying that the shear stress is related to velocity gradients, and that proportionality constant is the coefficient of viscosity. So we thought already about viscosity qualitatively as resistance to flow, but this is a more precise definition that we can use in thinking more precisely about what's going on in the flow and how the fluid responds to deformations. Because remember, on the first video, we said that one of the main characteristics of fluids is that they deform in response to forces or stresses, and so this equation, Newton's law of viscosity, expresses exactly that. So a couple of things here to notice. If this viscosity coefficient is constant, then the fluid is said to be Newtonian. And so often if this is constant, the Greek letter mu is used to represent this viscosity coefficient. So this is a material property just like, you know, density or thermal conductivity, any properties like that. The coefficient of viscosity is a material property that you can look up in a table. Now, for many other kinds of fluids, the viscosity coefficient may not necessarily be constant, and it's often the case that this coefficient depends on the rate of deformation, or this velocity gradient. And if that's the case, then the fluid is said to be non-Newtonian. So one example is a lot of polymer solutions, or polymer melts, surfactants. A lot of things like that are examples of non-Newtonian fluids, and a lot of times they exhibit what's called shear thinning behavior. So as you shear them at a greater rate, as you apply a deformation at a faster rate, then they exhibit less resistance to flow. The viscosity goes down. So that's just one example. But any property where the fluid's viscosity changes or depends on the rate of deformation is an example of a non-Newtonian fluid. Okay, now what did I mean when I write tau yx here? That's important to clarify. So here I'm kind of blowing up a plane in this flow, and I have two different things drawn here. So this n is what's called a normal vector. So this is a unit vector that's normal to the surface, and then I've shown the velocity vx. So this is going in the x direction. So tau yx, when I write this, it means the shear stress on a surface whose normal vector is oriented in the y direction due to a flow or a force that's acting in the x direction. So that's what these two indices mean, because notice that if I need to describe the state of stress, I need to know not only the direction of the applied force, but I also need to know the orientation of the surface, because both of those quantities are necessary for me to describe the state of stress. So that's why I need two indices here to describe that. So let me write that down here. Tau yx is the shear stress on a surface with normal in the y direction due to a force or a flow in the x direction. So that's important to keep in mind, because we're going to use that when we get to the conservation of momentum. So this is an example of a tensor quantity, right? We need 9 components to describe the state of stress, because it depends on both the orientation of the surface and the direction of the force, both of which are vector quantities. Okay, now that we have some idea how to think about viscosity in terms of the relationship between stress and deformation, it's useful to kind of think more deeply about what exactly does this coefficient represent. Well, thinking back to our description, or at least qualitative description of viscosity in terms of the resistance to flow, we can imagine that this viscosity coefficient expresses interactions between fluid layers that can transfer momentum between them. So what kind of interactions can have this capability? Well, if you go back to our discussion about liquids, solids, and gases, remember that in the case of liquids, you have this situation where you have these weak cohesive interactions. So you can imagine that if you apply a deformation to a liquid, these weak interactions will break, but they may locally continually break and reform during the course of the flow. And so this is exactly kind of a good way to think about the kinds of interactions that can be capable of transferring momentum between fluid layers, because at least for short periods of time when these interactions form, then momentum will be able to be transferred between different layers, between neighboring layers or neighboring molecules in the fluid. Another thing that we thought about in terms of gases mostly was this idea of random motion or interactions by collisions. So you could imagine that in a gas you have these this random component of the motion. So if a gas molecule from one layer comes into contact with a molecule in another layer, there's a collision, and then some energy or some momentum is transferred between those layers as a result of these collisions that continually take place between layers. So these kind of pictures are qualitative. They're useful to have in our heads to imagine what's going on, but they also do explain what we observe in terms of the temperature dependence of viscosity. So for liquids, we observe that as we increase the temperature, the viscosity goes down. And this makes sense because at high temperatures, these weak interactions between molecules will become even weaker, because the thermal motion will become greater of the individual molecules. So that further acts against these weak cohesive interactions. And so a typical example is pancake syrup. You go to a restaurant that serves pancakes, and the syrup often is served heated up. And when the pancake syrup is heated up, it flows very easily, almost like water. So that's an example of this kind of property. As we increase the temperature, the viscosity goes down because these interactions, these cohesive interactions between molecules in a liquid, become weaker. In a gas, that's kind of more representative of the second case. So gases, the molecules are interacting more by collisions, So for gases, we observe that the viscosity increases as the temperature increases. And this makes sense because as you increase the temperature, remember that's a representation of the internal energy of the system. So you would expect to have more collisions and more energetic collisions as you increase the temperature, so that there would be more opportunity or more capacity to transfer momentum between different layers of the fluid. And that's what's observed as the viscosity goes up with temperature for gases. So liquids and gases actually show opposite behavior in general with opposite dependence on temperature. And we can explain that based on these ideas about how individual atoms or molecules within the fluid would interact and be able to transfer momentum between layers. So this is what we mean really fundamentally when we're talking about viscosity.